В общем, здравствуйте всем. Очень рада, что все собрались здесь. И для меня неожиданно много народу, потому что лето, и мне казалось, что все уже разъехались. Но все-таки собралось довольно много народа. И прежде чем Виктор начнет, доклад будет делать на английском языке, но вопросы свои, какие-то комментарии вы можете говорить на русском. Вот, что удобнее, мне кажется. Я предлагаю вначале нам всем немножечко познакомиться с вами, потому что мы тоже из разных мест, кто-то из университета, кто-то из других мест. И поэтому давайте коротенечко каждый скажет, откуда он и насколько, что он знает про САГУ, знает или не знает, пользовался, не пользовался, то есть какое отношение имеет к геоморфометрии и к САГе. Все, спасибо. Я могу начать с себя. Я могу начать с себя и запустить цепочку. Меня зовут Женя, Евгения, я выпускница кафедры картографии в 2009 году. С геоморфометрией я сталкивалась, конечно, непосредственно, писала работы по геоморфометрии, с САГой, в принципе, тоже знакома, работала с ней. Как-то так. Можете продолжить.
Меня зовут Майя, я студент 4-го курса географии института кафедры картографии и информатики. С вами я не работала, но с геоморфометрией сталкивалась.
Меня зовут Дима, я тоже студент 4-го курса кафедры картографии и информатики. Ну, про САГА я слышала, но не работала.
Меня зовут Никита, сейчас я работаю в Кануксе. Геоморфометрии сталкивался и работал с ней, когда учился в аспирантуре. То есть активно интересовался этими и программными продуктами, методами.
Ты больше не учишь, что ли? Уже зачислился?
Это не взаимосвязано.
Я занимался
неприступным барьером перед защитой инопланетян.
Да.
Кто следующий?
Ты?
Дима, ты?
Да. Меня зовут Дмитрий Барышников, я сотрудник компании СГИС. Сами, естественно, работаем, и программируем, и так далее, геоморфометрии, я в своей работе не сталкивался. Как раз я послушать с нами.
Максим, ДСГИС, САГу только что установил.
Артем, сотрудник компании NextGIS. С SAGA я тоже не работал. Вот интересно, что это такое.
Я сотрудник лаборатории Семинара, кафедры геоморфологии. И с SAGA я тоже не работал, но интересно узнать, что это.
Айно, я аспирантка кафедры геоморфологии, тоже хочется познакомиться, поэтому присутствую здесь.
Евгений, сотрудник кафедры картографии и Государственного астрономического института имени Штернберга. Много работал с своими моделями рельефа, но вот геоморфометрией занимался мало, поэтому соответственно, в САГе практически не работал. Я не знаком с ней, поэтому очень интересно быть на этом семинаре.
Меня зовут Светлана, я геоморфолог, поэтому приходится сейчас сталкиваться с геоморфометрией. О САГе слышала, но больше раз не приходилось.
Давайте, я закончу.
Меня зовут Ярослав, сотрудник компании АТЭР. Про САГу слышал, но с ней не работал и геоморфометрией тоже не занимался.
Меня зовут Оскар, сотрудник кафедры картографии. САГа не работал, вот пришел на
Меня зовут Максим, я выпускник кафедры геоморфологии и палеогеографии 2013 года. В данный момент работаю в лаборатории эрозии почвенных процессов. С цифровыми моделями рельефа приходилось работать, но вот о САГе я слышал позавчера только.
Я Аня, студентка кафедры картографии, с морфометрией почти не работала, с САГой тоже.
Меня зовут Тимофей, я сотрудник кафедры картографии, с САГой работал, но совсем чуть-чуть, поэтому надеюсь, что узнаю сегодня гораздо больше.
Ну, а я зав. Кафедрой картографии и информатики. Вот так случайно получилось, что мы проводим семинар еще вчера, не подозревая об этом. Вот. Геоморфометрией кафедра занимается очень давно. И когда еще только начиналась автоматизация в картографии, у нас ребята сами писали, выпускники мата, писали свои программы на всех языках, которые только были, начиная от Фортрана. Вот. И есть очень интересные наработки, которые связаны в основном, ну, так сказать, с достоверностями моделирования и с разработкой способов представления. Если останется время, я вам покажу иллюстрации, как вот эта 3D-визуализация, на которую накладывается углы наклона, освещенность, значит, реки, сразу все параметры там участвуют, и насколько наглядным становится изображение формы рельефа. С SAGA мы столкнулись совсем недавно, то есть слышали, и я лично много там посмотрела публикации, старые гайды, которые были, потому что мы в основном работаем в Ардисе, а задачи у нас связаны вот с более тонкими всякими вещами, с рельефом и с построением, ну, с гидрологическими приложениями. И, значит, по литературе я поняла, что набор функций вот этих гидрологических в SAGA существенно больше. И там больше всяких вариантов. Вот. Но вот поскольку мы как бы вот, нам поставили пакет, и мы за него отвечаем, за АРГИС, поэтому мы стараемся свои какие-то, вот сейчас вот у нас со студенткой даже разработали алгоритмы там через дифференциальное уравнение, через балансовые, сделать практически то, что в SAGA делается почти на автомате, я так понимаю. Вот, поэтому очень интересно пообщаться, посмотреть, в чем отличие, и принять решение полностью мы, допустим, переходим на открытый пакет, или мы все-таки даем студентам, мы стараемся давать, ну, в общем, хоть мы не сидим в АРГИСе, но стараемся давать разные способы работы с пространственными данными и больше учить не функциям, а вот методам геостатистики, геоанализа, геомоделирования, вот такие всякие вещи. Ну, вот очень интересно, потому что в этом году у нас одна работа защищалась чисто. Вот мальчик анализировал возможности SAGA для моделирования рельефа, и он будет продолжать, он еще только 3-й курс закончил. И вот вторая девушка, которая сопоставляла возможности SAGA и АРГИС. Так, что это?
Открыто должно быть.
Наоборот, да. А там сейчас больше стучать не будут, можно оставить, а то мы здесь записываем.
Вот есть там один компьютер, он свободный. А вот насчет еще одного, я
нет, там в углу не преподаватель будет.
Я просто послушаю. Ну садись вот сюда, садись. Я бы сейчас послушаю, я не буду.
Ну, по ходу дела кто-то начинает слушать, а потом, если интересно, значит, с компьютером и к своему ноутбуку. Ну и мы предоставляем слово.
Okay, so it's my turn. Sorry for doing this in English. If there's anything you don't understand, just feel free to stop me when you don't understand something. I'm going to tell you something about myself, as you did. The reason why we are going to talk about SAGA is because not now, but since in the past I was part of the SAGA development team, so I mean I was part of the people writing SAGA. I'm not anymore into that, but my story with SAGA starts when I became part of the team and started working with SAGA. But one of the worst things about SAGA, one of the bad things, is that there's no help at all. Right? Those of you that you have probably tried the software, you have probably seen that there's no help. There's a button, you click on help and it says, yeah, there's no help. Okay. So I started using SAGA, I kind of became proficient in SAGA, so I could just do most of the things I'm going to show you here. And people started asking me, so one day I became tired of explaining that and I started writing a book about SAGA, which eventually became the official manual of SAGA. So that's how I got into that. People started using that and I got more involved into SAGA, and well, eventually I ended up collaborating in this book, that I have copied this to you in this folder. You're going to find the detailed elevation model that we're going to use, and also this book. This book was published in 2008, if I'm not wrong. And well, it's a book about geomorphometry. We are definitely not going to see everything that is in there, but it's a book about geomorphometry, both the theory and both the practice, just how to do that with software. And I contributed 2 chapters to the book. One, it's about theory, it's about basic morphometric parameters, and the other one is about SAGA, how to do geomorphometry in SAGA. So actually, all that I'm going to tell you in here, more or less, you can find it in the chapter that is called Geomorphometry in SAGA in the book, right? If you want a paper copy of the book, you can just browse and just check for it, and you can buy the book. But I'm giving you the book for free, okay? So you can just check it and right. Okay. So we're going to work with SAGA. We're going to work with the book anymore. So we're just moving. If you can open SAGA, it should be installed on your system. You said, most of you, that you have heard about SAGA. Some of you have tried it a little bit. So we're going to start just a quick introduction about the main areas of SAGA, because I assume that most of you are familiar with, maybe not SAGA, but ArcGIS or QGIS or something. Everyone has used GIS, you know the difference between a raster layer and a vector layer, things like that, right? Okay, so SAGA is not so different from a normal GIS, but there are some things that are different. Some things are different for good, I mean it's advantages. Some of the things are different and they're not very good. Okay, so I'm going to show you both of them. And then once you become a little bit familiar with SAGA, we're going to move to the actual analysis and just do some geomorphology. Okay, so the first thing we're going to do is open some data. And in that folder over there, you should have just one single file, which is a detailed elevation model of region in Spain where I live. And we're going to open that in there. And you should have something like that, right, in SAGA with all the windows open. Then we're going to close some of them because there might be a bit of space, a lot of them, a lot of windows. But at first you have several windows, and the window that we are going to use is this one in here, right, which is the data source. And just basically have to locate the file that we're going to open and just double click on it. It's pretty easy, right? So if you just close that, if you don't see that in window here, you can click and activate the show data source window to show this, right? So once you have it, you just go to the folder where you have your data, and you should have this dm25.tif, right? And this is the file that we're going to have. SAGA doesn't support a lot of file formats. Actually, for raster files, it supports just its own format, which is called sgrd format. But then there are a lot of models. Everything in SAGA is accessed to models. Okay, all the functionality is into this list of all the things, and you see the import-export models for different formats. But natively, it just supports its own format for raster and shapefiles for vector. Right? But if you just access things through the data source window, it will make a conversion. Right? So basically, just double click on it. If you don't see anything, or you can give me a small face. Say something. Okay, anyway, we're going to go. Okay, we're going to go the other way anyway. That's what I wanted to tell you about the formats. Some of the formats are not supported here. So we're going to do it through a model, right? So this is the list of all the, there are two ways of accessing all the algorithms and things that we are going to use. One is through this list, modules, and you see that they have different levels of nesting, like you can go, 1, 2, 3. And then the other one is just this list in here, which is the same algorithms but with a different classification, right? So I prefer this one. Some people prefer the models in here. I just prefer that one, but you can just go wherever you want. In this like file, read, import, and here you can just select the kind of files that you want to use. Right? So this is what we are basically going to do. So I can import the image, right? What I want to do is to import the image, that dm25.tiff. Right? So basically I can just select from that one. Okay. Image file. Just search for the file wherever I have it. Yes, this is what we're going to find in all the models that we use in SAGA. Is this kind of table, okay, with only 2 columns. In the column in the left, we have the name of the parameter. In the column in the right, we have the value of the parameter. It's always like that. If you use maybe to AutoCAD, it has this similar kind of interface, right? That's it. Oh, great. Hey, we're having good time here. Yeah, that's loaded. Hello. Let me check again. Yeah, we're not doing really good. 1, 5, 3, 4. Yeah, should be that. Okay, this is bad. Did it work in your computer or not? Did it work? So you can open the file actually? No? So some people can, some people cannot. I mean, I had this loaded before. Like, I had a project with this file loaded before, and I just loaded it. By the way, you have to enter this big thing. Whenever it finishes doing something, this other column in here has the settings and things. So if you just go to the module library in here, so you select this, in here you're going to see some settings that you can use. And the first one is big when finished. If you please turn that off, because otherwise it's going to be big. Okay, let's try again. We should have this.
Жень, а у тебя там твои данные, они не к какой-то директории были привязаны?
Нет, но это просто тип лежит. А мы через раз
ссылка может быть на какой-нибудь.
Да нет там ссылки никакой, там просто файл лежит. Чистый файл. А у кого не получается? Можно говорить как-то через грид открывал или просто тип?
File, and image. You did it that way, yeah? No? Okay, then. From there, yeah. That's what it was trying to do at the beginning, but it didn't work. You just double click on it and Yeah, but I haven't. I mean, this should work just by double clicking on this. This should work. Let's open it.
И там дальше нажимать кнопку «Добавить карту».
Теперь вот здесь тоже. Я уже 4 раза. Да, просто.
Я буду давно отметить работу через внутреннюю
Смотри, через дем 26 нажимаешь и она открывается. Вот нижний 25-й.
Да. Ну давайте подвижем.
Наводишь на файл, правой кнопкой, там появляется меню строчка АДД туннель. Нет, 2 раза.
Нет, 2 раза на 25 тип. Вот здесь внизу. Вот, да? Да, еще раз 2 раза.
Я не понял.
Нет, 1 раз жмешь.
Работает. Что происходит?
Там он один раз матерился.
Okay, so who's having problems with that? What we have done is just in one computer that can open it, then we have exported it to the native SAGA format. You should be able to open it now. It seems that everyone can, except for me in my computer. Everyone could open it? I'm the only one that is having that problem.
Ребята, а сзади как? Видно, что там происходит крупнее? Нормально, да? Вот можно разрешение еще отменять.
Чего? Что-то не быть? Через шит
Где? Он ушел.
Voilà. Okay. Okay, you should have something like that, right? Okay, so this is what we're going to use. We just need that, nothing else than that. Okay. And what we're going to do is just perform analysis on that deceleration model, right? And just to become a little bit familiar with SAGA, now we can close the data source in here. And one important thing in SAGA that is different from other geographical information systems is that the data and the rendering of the data, they go separate. Okay, if you have ArcGIS, you just open ArcGIS and all the data that you open, you're going to see actually, right? If you add a deceleration model, you have a representation. And here it's not like that. We have one, you see one of the tabs called data, and that is all the data that I have. And then I have one called maps, which is the actual representation of the data, right? But I can just close it And you see I have no representation, nothing that I can see actually, but the data is there, right? Okay, so that's important. Whenever you want to see some data, you just double click on the data, and then it creates one view. If I want to visualize it again, I just double click on it, and then I say, okay, I add this layer to this map in here, or I create a new one. Okay, let's create a new one. And then you have it. So it's separated the visualization and the data itself, right? So actually we can do everything we're going to do, all the analysis, without visualizing it, right? It's important to understand that. It might be a little bit annoying, because if you don't take care and you have 20 layers, you might end up having 20 different windows, okay? So if you just go too fast and go, okay, let's visualize that new, now you have to put it into another one. Okay. So we have this tab in here with all the data, and another tab with the maps, right? And now what I told you, depending on what you select in here, whatever you select in this part in here, you're going to see the properties of that element in the other side, right? So in this case, I can just click on my deep elevation model, and then I see here all the properties of the deep elevation model, right? And I see that I guess that some of you have already found that, because one of this is the rendering, how we put the colors to that, and we have this colors in here that we can change. By default, it will show this color run, but we can change it as well. We can just go in here and edit that. We can invert, or we can just have some presets and select one. Like we want it to go from topography, right? Okay. Now we click on apply, and it's changed, right? So this is the way we can interact with everything. We can just click on it in here and then interact with the properties on the other side. We can do that with the models as well, so we can select an analysis model in here and just change the parameters we need on the other side. I'm not going to use it that way because I don't like it that way, right? I'm just going to double click actually. So you see in this one, import text table, I have the things in here, but if I just double click on it, I see the same thing in here in a separate computer, right? Might be a little bit confusing, but it's just okay. So once we have set up the rendering and the basic properties, we can just get rid of it. Okay. So we have more room for just the visualization. Everyone understand that more or less? So you can open data and then just browse things on this part, that I have on the left part. There's the manager, which contains the data, the maps, thumbnails, etc. And then we can just have the properties in the other window, but I'm not going to use that. I'm going to go straight. Okay. So we can start with some simple analysis, right? There are two main blocks of analysis that we can, two main blocks of so-called morphometric parameters. One are the local parameters, and one is the regional parameters. I don't know if you, those of you more familiar with geomorphometry, local parameters are those parameters that just depend on the value in the cell and value in a surrounding circle of the cell, a closed area. And those regional parameters are those that depend on a larger area, right? That is not always the same. For instance, the slope is the local one. We just analyze the cell and what is around. But parameters related to hydrology depend on the cell and all the ones that are connected, where water flows into that. Okay. We're going to start with the easiest one, with the most simple one, which are the local ones. Right. Okay. This is the typical thing that you can, select this pan in here, and you can pan and you can zoom. I guess I don't have to explain that. You can just do all that, right? So I'm not going to describe much about this, about the visualization, the maps, etc. I'm just going to go a bit more directly to the analysis. So the first thing we're going to do is calculate this local parameters, right? We're going to calculate slope, aspect, and then curvatures, which are not so popular maybe as the slope, but they're pretty interesting parameters, right? So you see in all the groups, all the algorithms that we have in here, there are quite a few that start with terrain analysis, right? These are the ones like terrain analysis, geomorphometry, they're more or less the same thing, right? So these are the ones we're going to work doing most of the time today. And this particular one called morphometry, which, as you can see, it contains plenty of algorithms. Of course, we are not going to see them all, But the idea is that you get a little bit familiar with SAGA and then you can explore them yourself, right? With this and along with the book, you can understand what each parameter means, and then you can just run it from it. Okay, so that's the idea. And you can see that there are quite a few parameters in here, and this one also aspect crop. And you see it's the same as when we imported the data. It's kind of similar. You have two columns, values, name of the value on the left hand side, the value actually, the actual value of the parameter on the right hand side. Right? And let's go explaining what that means. Whenever you're going to use a raster layer in SAGA, you're always going to see that thing called grid system. Okay, what is a grid system? When you have to combine several layers in SAGA, they have to be exactly the same, have exactly the same area and exactly the same number of cells, right? And if I go to the data in here, you see the detail elevation model that I loaded, it's in this grid system, which means it's 25 meters, the cell size. It has 601 multiplied by 410 cells, so that's the width and height of the layer, and this is the coordinate of the lower left corner. So if you have any other layer, like if you put it into the, and it doesn't have the same grid system, then you cannot combine them, right? If I have to do any operation that takes two raster layers, they have to be the same. They have to be in the same grid system, right? Okay, so that's important to know because you might take one, let's say raster layer, the detail elevation model in this grid system, and then someone gives you a layer with soil data. So fine, you put it in here, and then you can use it together. You have to use some other algorithms to put them in the same grid system so that you can just, they match one to the other. In this case, it's not important because we just have one raster layer, so we're not going to use several. But whenever SAGA is going to ask you for a raster layer, it's going to ask you for a grid system, right? So you see in here, I have in this field here, I have to enter the elevation, right? The detail elevation model, but I have no DM to select from. It's like there's no raster layer where there is, but first I have to tell SAGA about the grid system. It's like in this grid system, and now it populates this with that. Okay, so there's not just one simple thing that you have to select, just the layer. No, you have to select the grid system, and then from all the layers available on that grid system, you select one. Right? If you see this kind of arrows in that, if they're going to the right, that means that it's an input. If they're going to the left, that means that it's an output. And if it's a double one, it means it's mandatory. You have to enter it. Okay? And if it's just one, it means it's optional. So in here it's like there's one mandatory input, the elevation. There's two mandatory outputs that it's always going to generate a slope and aspect. And then there are some optional outputs that is curvature, plane curvature, and plot line curvature. Right? We're going to generate them all. Create. Okay, make sure that you don't select in here the DM. Okay, you see that you will have in the outputs, you have the option to create. If it's optional, you have create and not set. And also you have all the other layers that are available. Why? Because if you select one, it's going to overwrite it. Okay, so make sure that you don't select the DM because otherwise you're going to lose your DM. Okay, the slope is going to end up onto the DM, right? It's going to leave. So we just say create and it will create a new layer. Everything that you create in SAGA is temporary. That means that if you're used to ArcGIS, when you do like, let's do a buffer. When you do that buffer, you have to enter file path, right? It goes in here, in C, whatever. Not in here. In here, everything's temporary, okay? SAGA takes care of putting it wherever. And then when you close SAGA, it will say, hey, you have created temporary layers, but you haven't saved them. You want me to save them, and then you save it to a file. But if not, you just can forget about it. So in this case, I don't want to keep the data in here. This is just for the course, just for the seminar. So I just need to calculate everything, and I don't have to worry about entering any file, right? Everything is temporary. Okay, so let's see how to fill that. We select the grid system, we select the elevation, then we put all this to create, right? And now this is the last thing, the method. There are several different ways. This is very typical in SAGA. there are several ways of doing almost everything. If you have used the slope calculation in ArcGIS, you just have slope. Here, you have anything else. Just slope, and that's it. Not in here. Usually in SAGA it has a very academic or very scientific approach that if you can see, you know, all those papers by Travis, by Tarbutin, they have published different ways of calculating the slope, then SAGA tries to implement as many as possible, right? So it's something that is a little bit more complex. You can always use the default option, but if not, you're going to have more options than what you're going to find in something like ArcGIS or whatever. Right? So what is the difference? Some of you are familiar with geomorphometry. Someone knows basically which are the differences between those methods. Okay. Well, basically there are two ways that we can calculate slope. One is like a very simplistic approach. What we do is just this. Let's go outside. I'm going to show it to you. A little bit of theory here. So open a new one. Well, this is, you just select on the map, and then here there's an option saying show cell values. You just can show cell values just to make it more clear what I want you to do. Because I wouldn't, just when you zoom close, you just zoom out, you're not going to see it, right? But the most simple way, the most simple way of calculating slope is like, okay, I want to know the slope in this cell in here, right? We are always going to work with raster layers, by the way. Like, then we're going to see a little bit about teams, but most of the things that SAGA can do and most of the things that can be done in geomorphometry, like the things you're going to find in the book that they gave you, they're done based on raster layers, right? So we want to calculate a slope layer, and we need to know the slope in here. So which is the most typical and easy way, the one that you can find, by the way, in ArcGIS, etc. Is just you stay here, and you calculate this slope, and this lines to all the surrounding cells. So I take this line, you take the distance between these two cells, which is 25 meters, right? And you see the difference in elevation, it's 4 meters. Then it's very simple trigonometry, and you can calculate the slope. You do it like in 8 directions, and you just take the highest, the largest one. That's very simple, okay? That's called the D8 method, deterministic 8, which is like very simple one, but you know, it's like where is the maximum slope? It's this way, this way, this way. Very simple one. And if you go to our, and here you can see that you have this method, right? It's called maximum slope. Okay, here it's the oldest one, it's the most simple. This one is similar, maximum triangle. A bit different, but kind of similar. And then you see the other ones that are more mathematical. What they do is just take the central point and all the other points, and they adjust the plane, calculate the equation of the plane, and then they use differential geometry, that's mathematics actually, to calculate the slope and the corridor, right? So the first and the second methods, they're very basic, and they don't have a real mathematical base on the ground. But the other ones, yeah, they fit a different kind. You know, there's like second-degree polynomial or third-degree polynomial. But there's a slight difference, right? But basically, that the idea is that you calculate in each group of 9 cells, okay, that small square of 9 cells, you calculate the equation of the plane that passes through them, and then you just do mathematical operations. Right? The slope and the aspect, they correspond to the first derivative, right? And the corridor, that's the second derivative, right? And we're going to see that. So we just select the one by default, by the way, is the one that in the literature it's found to be the best one. Okay, the Semberg. Okay, there are a couple of papers that say that that's the most accurate. And now we go to data. Yeah, someone hasn't turned it off. I say it again, throw some modules in here. Now, object properties, and you click on that one and see viewpoint finished, and you turn it off, or turn the volume off. on your computer, right? If you don't want to hit a big each time, you select your model libraries, and here you see big when finished, and you just turn it off and then click apply. Okay. Okay, so we have our first results. We can go to our data, and you see we have been working with our DM on our grid system, and everything that it has calculated is on the same grid system, right? You see, it's on the same grid system. That means that now we can use all of these layers together because they share exactly the same grid system. They have the same size, they have the same number of cells, they're placed on the same area on Earth, exactly the same, right? And you see, we do not have any visualization of those layers, right? We don't have anything. Because data and visualizations go separate. If I want to visualize any of them, I just click on it. Let's have a look at the slope. Double click on it, and you add a new view. And that's the slope. Okay. In this case, the default color palette is different. It goes from yellow to red, red indicating more slope. And here you see you have some basic statistics, like you have in here. This minimum and maximum value used for the representation of the actual minimum and maximum values of the data. So if anyone has any question, please do that. Okay, we're going to
Склоны градусов, слово градус.
Okay, yeah, let's have a look at that. Actually not. Did you see that? Well, there's one important thing. That's true. Let me check. I don't know if it was. Yeah, actually it's percentage. You know that? No, percentage. If I'm not wrong, that's what they're saying. But there's one thing that's important because when we see some other algorithms that take slope as input, it has to be on that same unit. So if, for instance, you don't have a DM, but you have someone gives you a slope, and it's in a different unit, you cannot use it. So that's important. But yeah, in this case, it's right. There's one model in case you want to check. There are models for doing many things in SAGA, and there's one to convert units. I'm not sure what it is. But let me see if the tools probably. Yeah. Grid calculus, maybe. Metric conversion. Okay? You have this one, and it counts to radians, 2 degrees, radians, whatever. No, actually it's degrees. Yeah, you were right. It's degrees, not percentage. Yeah. So in case you want to convert to radians, we're doing something like this. This is because if you have used an older version of SAGA, it did everything in radians, which is a bit awkward. Because, yeah, radians are good for computers. Okay. So let's go opening the layers. And we can have a look at this aspect. This is pretty, this looks like the typical representation that maybe you have seen that is called a shaded relief. I don't know if you're familiar with that, what a shaded relief is. It's an illumination model. We're going to see that. But this is not actually an illumination model, but the thing why it looks like that is because if you go to the palette, you see that it's a circular palette. You see that the coloring here is the same as in here, right? Because 0 degrees, the orientation is 0 degrees, that's north. And it goes all the way up to 360 degrees, which is north again. Okay, so that's why this coloring here is the same as this coloring here. And it gives that, that appearance of being like a shaded relief. Right? But it's just because of the color, it's not an actual shade. Right? And here this is degrees, of course, and you see that it goes from 5 to 360, which is 0 means north, as I said, and it goes like clockwise like that. So south is 180, and west is 270, and then back north at 360. Right? Those are parameters that probably you can understand, right? Slope, aspect, and prism. What happens if you calculate aspect? Let's do that. Yes. So now let's say that I want to rerun the model again. I won't run it again. But you see, by default, it selects the layer that I have created. So it's not going to create a new one. It's going to change the one that I did before, right? So if I say, let's try a different model. Let's try the maximum slope one. If I want to generate new layers so I can compare, I have to change it in here and say create. Because otherwise it's going to override the one, right? And you can see that if it's being represented, it's going to change right in front of your eyes. It's going to change. I'm not going to do that. I'm going to just leave it like that. So I select maximum slope. And you see, it has changed. You know, the values are different in this case. And actually, closer, let's go to presentations. Here. Yeah, you see the value range is the difference. And we have a look at the values. Yeah, have a look at those values. Now the values are not continuous. There's not 0, 1, 1.5. No, there's just 8 different values. Right? Why? Because we've been analyzing the direction of the maximum slope. So if I'm here and the maximum slope is this way, then it's 0. If it's this way, okay, so there are multiples of 45 degrees. Right? 0, 45, 90, there's no intermediate values. Right? So that you see the difference between choosing one algorithm and the other, it's really big in this case because in one case it's continued and in the other one it's like that. So it's just like you have just 8 different options, 8 different values. Right? If I just calculate again, but this time I use again the Stevenberg algorithm, you see the values are different. You know, there are not 2 cells with the same value actually. But in the other case, yeah, there's like 8 values. So here you see the difference between the mathematical model and the other very simplistic approach with calculating slope. Any question? Fine. Okay. So let's move to the next one, which is probably something that is not so so common for you or not so familiar with, which is curvature. Anyone knows what curvature is? Actually? Yeah, you're familiar with the idea or not? Yeah, the rest of you just like no? Or yeah, everyone knows what curvature is? Should I explain that? Or okay, well I'll explain it a bit in case. Basically, curvature tells us not the slope, like the slope or the aspect, which correspond to the first derivative. The curvatures correspond to the second derivatives, and basically tells us if the terrain is concave and convex, right? So basically, it's going to tell us a lot of things about how the physical processes work on that area. And why are there different kinds of curvatures? Because there's no curvature at a single point. When you take a point, there are infinite curvatures. And the curvature is defined by the surface and a plane. So you have to put a plane and cut it. Right? You cut the terrain and then you analyze if it's convex or concave on that plane, right? So which are the most important planes? The plan and the profile curvature is basically, if I take the plane that goes in the maximum slope, okay, so if I'm here and I'm facing the slope and I take this plane and then I analyze if it is concave or convex that way. And then the plane that goes like the contour line, that's like exactly like that, right? So I see if it's concave or convex, right? So what does the curvature tell us? If I have a plane curvature, that means that this plane curvature that is concave, which basically tells us that when the water flows down, it's going to stop, right? Because the slope diminishes, right? If this is convex, it's just the opposite. If water goes this way, it's going to start going faster because it's more slope each time, right? What happens with the profile and the curvature? If I just take a profile curve, and if it's concave like that, what that means is that you have water flowing in here, it's going to converge. So that means that I have a little bit of water, it's going to become more water, right? It's going to actually become something like a small river. What if it's the other way, and if it's convex? Then the water is going to diverge, right? So then we can use all those parameters all together to classify the terrain. To say, okay, in here the water is going to slow down, and then it's going to diverge. So probably it's going to create sediments, right? So this kind of thing, this kind of analysis we can do. And if you just represent one curvature in here, well, you see, in this case, there's a divergent palette, which goes, you see there are positive values and negative values, and this is the scale. So if it's white, it means that it's mostly no curvature, it's like flat. And if there's -1, which represents a concave curvature, that's blue. If it's a convex one, that moves towards red. Right? So that's what you have in here. And well, that's it. You see, in the areas where we're going to have more rivers or where water is going to converge, we have those blue values, right? And in the areas where actually water diverges, we're going to have So that's the idea of the curvature, which tells us if it's concave or convex, but in a given plane, right? We have to take plane. The two most important planes are the one that goes in the maximum slope line, and the other one is the one that goes in the profile line, right? Okay. So let's calculate one parameter that gives us the same information, but in a clearer way, right? Which is the convergence index. We do a similar analysis, and we just go to maps. We just take the cells in here, and in the surroundings we just see which of those cells actually flow into us, right? We just calculate the slope in each layer and see if they flow towards us or just to go somewhere else. And we have this convergence index, right? And let me show you what it looks like. We just go to morphometry, and we just select the convergence index. There are two different ones. One's called search radius, so we can make a bigger radius and analyze more, but the simple one's fine. Right? And you should be able now to feel that yourself. We select the grid system, of course. We select the elevation, which is mandatory. You see the two arrows in there. Now we select DM, don't select any other ones. You have more options now. And you create a convergence index. And there are two methods as well, but you can use the default one. So, that's such a big picture. Oh. And we have a new data that we can actually represent. Okay. You see it's similar to the curvature. It's not similar in the way it's calculated, but it's similar in that it gives us the convergence. And this is a very interesting parameter because now we're going to move into those regional parameters. Those are parameters related to hydrology, okay, that analyze not what is just close to itself, but all that is linked to that, where it flows. But in this case, this is a local analysis, but although it's a local analysis, you can clearly see where is the river, the main river, right? This is the main river, and actually, this analyzing what is around you, you don't have to look any farther. Just by analyzing what is around you, you can just know where the river is going to be, which is pretty fascinating, because, I mean, it's easy to find out where the river is if you analyze all the flows. If there's water, there's going to be river. But just analyzing locally, you can see if you're in a river or not, actually, which is like a very interesting thing. If you see this, the areas in red, right, these areas in red, they represent actually the area that is on top of the mountain, right? You know, there's like the beaches on top. And on the other hand, the ones that are blue represent the areas that are in the bottom of the valley. So there's a convergence actually on that, right? Okay. So this is a very interesting parameter. Okay, those parameters and many more that you have in here are part of those local parameters. As I said, it's just when you do that, you just analyze for a given cell, you just analyze that cell and the age around it. That's it. You don't look any farther, right? If I want to calculate that parameter in here, I just look in the surrounding, nothing else, right? Now we're going to move farther and we're going to analyze all the cells that are related to one, right? Related, hydrologically related, right? The water flow. And to make it that a little bit more visual, we're going to calculate a vector layer that allows us to see that. And we're going to go to the channel. And this should be one. don't know if it's here. Because I want to calculate like a very dense channel network that actually contains all the simple links between cells. I don't know if that was in here or not. It seems that I don't have that model. There was one model called DA, which uses the DA method actually. It seems that it's not here anymore. Yeah, well, anyway. Yeah. Well, there was one that, we're going to see several different methods now for calculating this hydraulical parameters. One, it's a very simple one based on the E8, which is eight directions. And there was a way of calculating that network that I haven't seen. Okay, anyway. That was more easy to visualize that. But what we are going to do is just we stay at this cell, right? And we just take the maximum slopes, right? As I did before, we calculate all the 8 slopes, and then we take the maximum, and then from this layer, from this cell, it goes to this one, right? And then I do the same here. I calculate the slope in this, and from this one, the maximum slope is that way, okay? And then I do the same. So that way, what I can do is like, if I drop a drop of water in here, I can analyze how it is going to move, right? So this is the most basic idea, because, well, water doesn't move like that. Water can diverge and converge and can move in any different angle. This is a very simplistic approach, but that way I can just track the water as it moves, right? So what I'm going to do is do that calculation, calculate how water moves, right? And then I do it upslope. I do the other direction. What I say is I'm standing here, right? I don't want to know where does water goes from here, but how much water comes from uphill. Right? So I just track all those things and I see how much water reaches me. And that's what is called the catchment area. Right? That's the idea of the catchment area, which is a parameter that is the most basic parameter for hydrological analysis on a detailed elevation model, and that is going to be used in many different places here in SAGA and in any other software that has this kind of things. Right? So the catchment area is the area that I have uphill, and I basically do it just moving all the water from uphill and just calculating how many cells I have uphill, right? So I can just go and calculate the catchment area, but there's one thing that I have to do before. Always when you're going to work with hydrology, and a detailed elevation model, you have to do the pre-processing. That's very, very important. Why? Imagine that you see all these elevations that are around like 1,000 something, and imagine that this cell in here had an elevation of 900, right? What does that represent? That represents a hole, right? So if this, I have this 900 in here and 1,000 something in here. So where does water go from here? Nowhere, because it's always uphill. It cannot go up, right? What does it happen in nature? Well, water comes, fills the hole, and then keeps on going, right? But the algorithms that calculate catchment area and everything, they don't know about that. So what I have to do is fill these things, okay? All these holes, I have to fill them. So there's no way that I can find something that is below the other cells around, right? And there's in a part in here, you should see morphometry, pre-processing. You see there are different ways of pre-processing that fills things, different algorithms, the same idea as before. And always when you do hydrological analysis, you have to go through it. There are several ways of doing that. I'm going to use the most simple one, which is this first one, the function and Naku one. Right? But you can select any of the other ones if you want. But this is a very simple one. I'm going to use that one. And now I select in here. Yes. Select the DM. And here it's a very good idea right now. Don't use the create option. Just put the DM itself. And it's like, I have this DM, you're going to correct it, but just overwrite it. So I don't want to use the other one now. I'm just going to do hydrology. So in the next time that I need a DM, to avoid confusion, I just overwrite that. So I don't want to have like a DM and correct the DM. No, I just like correct it and overwrite it. So this is a good idea to put it like that, right? Okay. And what it's going to do is to replace all those sinks and all those holes with just flat areas. Actually, they're not flat. They're at least a little bit of slope, which is that minimum slope. Yeah, question.
But these changes are all temporary because we cannot change a raw file.
Yeah, it just changed in memory, right? I mean, if you have your file, your dem25.tif, that is not changed, right? Yeah, that's it. So whenever you open something, it goes into memory, or just SAGA handles that. But yeah, there's no way you can do that unless you go in here and actually you just go and you can actually export that, like save as, right? Otherwise, yeah. Okay, so we go back to the things. And I select my DM as input and as output. Right. Actually, this layer that I'm giving you, it's already preset, so there's not going to be any change at all. Still, some people have turned that off. Okay, so now you see there's no new layers, but my DM now has changed the name. Now it's named field and no sinks. But it's in there, it's the same one. Now I don't have a DM25 layer. I just have one called field and no sinks. Right? You can see it has overwritten the other one. And now you see that there's been no change in here, which is actually there's nothing to fill in this area. So there hasn't been any change. Now we can start doing hydrological analysis, right? I have field DM, there are no sinks. I'm sure that if I try to calculate the root, the waterfall, it's going to work fine, right? Otherwise, if you just find this, if there's a sink, when we try to calculate the root, we're going to see that we don't have a full channel, like a full river, but it stops in the beginning, in the middle, and then just starts again, and then stops, and then starts again. So we are not going to have a full channel. Right? So let's go to the catchment area here. And now they're the same as it happens with the slope, the same as it happens with the convergence index. There are many different ways of calculating that. They all get to the same result, basically. But there's, in the way the algorithm is written, the approach that it has, well, basically this flow tracing, parallel recursive. Yeah, that's like a very technical detail. You don't have to worry about that. Some of the parameters cannot be calculated with some of the approaches, and the parallel one gives all the results, so we're going to use the parallel one, right? And you see there are like a whole lot of results there. We can calculate many things, but most of them are optional, so we're going to start with the catchment area, because it's the one that we're going to use after that. There are other ones that we can calculate. So we select, again, our field DM now, it's not MDT25, it's DM25. And you see there's one optional, there's two optional inputs, sink roots. That's another way of dealing with the sinks and holes, is that I don't actually feel the DM. I use the DM with the holes, but then I give SAGA another layer that tells how water should move across the hole. So this is a more complex way, so I prefer just to fill it and fine. So we're not using that. And then you have one that is called weight. What is that useful for? I'm going to see how many area I have uphill, right? And it's going to tell me that area in area measurement, square meters, right? And here I have 25 is the minimum area. 25 is the cell size, so that means the area of a cell is 25 by 25, that makes 625. And the minimum value that I'm going to get is one cell, that's 625 square meters, right? If there's only one cell uphill, I have a value of 625. Right? What happens if I don't want those units? I can use a different layer with something different. For instance, imagine that you want to have not the area that is uphill, but the amount of sediments that I get, right? That they're coming to me with the water. But the sediments are not the same everywhere. right? So in this cell, it might be producing 1 kilogram of sediment. This other cell might be producing 1,000 kilograms. So what it does is instead of just summing up all the areas, it sums up the values in weight. Right? For instance, if you're going to calculate how much water you get here, you should take into account if it's a big basin, a big watershed, how much it rains. If it doesn't rain anything, okay, yeah, water is coming from there. You know, terrain is bringing me the water, but it's not raining over there. And over there is raining, then I should take that. So that's the idea of the weight, material, all that, but we're not going to use that. We're just going to use the elevation, and the result is going to be in square meters, right? Because my cell size is in meters, 25, right? That's the cell size of my grid system, right? And you see the catchment area, that's mandatory, it's always going to generate the catchment area. The other ones are optional, so I can just select them if I want, but I'm not going to use any one else. And now I have some options. I'm not going to discuss all the options, but just one of them, which is the method. Okay. You should be familiar with this D8 that I mentioned. That's the very simple one. This water goes in here and here. That means that if I drop 1 liter of water in this cell, it's going to move 1 liter to the next cell and 0 to all the other ones. But that's not how water works. You can put like half a liter in here, a little bit in there, and it goes that way. Right? And I'm going to show you with a more clear example now after that. But those are just different models. The best one in here is the multiple flow direction, basically, which just can move water to anywhere. So if water doesn't move just in 45 degrees angle, and it doesn't go in a linear flow, because it can diverge. Okay, we'll select it. Later I'm going to show you with more detail, which is now, you just believe me that this is the best one, right? Okay, so my field DM, then I have this grid system in here, multiple flow direction. I'm going to create catchment area. Let's go for it. And I can do it like that. So the first thing that you see here is that, well, I can see where the rivers are, but most of it is white, right? Yeah, you see, like, yeah, that's the river, that's blues, and that's white. You see the colors. I'm using 100 different colors, but it seems that there are like 2 colors, like, yeah, white, a little bit of blue, and just dark blue, right? Why is that? That's because the distribution of the values is a little bit weird. Most of the values are pretty low, and then there are quite a few that have very high values. All the water is accumulated there, right? And I can just either this, just right click on the layer, okay, and now do histogram. You see that's the histogram, which is, yeah, not very informative. You can just do zoom, okay, with your mouse, and you can just go up. Now, with the right click, with the right button, you just go up there. But you see there's nothing in here actually, but that's because most of the values are actually very low in this area. You see, most of the values are very low, and then there are quite a few that are very, very high. But there are so few that you don't even see them. There's like, there's quite a few there, right? And that's the reason why I don't see like the full color palette. What can I do to solve that? It's pretty easy. You see in here. Okay, yeah, this is one thing that's interesting about SAGA, that I can actually in the histogram I can select I can actually select here, and then it changes the way things are represented, right? I can just select one area, and you see that it uses the color just within that area, right? So, there we go. So what can I do to make this look a little bit better? What I can do is, instead of using this linear mode, you click on the catchment area layer, and instead of linear, you go and click logarithmic, right? And then you should go like that. And you see that the more that you get in here, more you change that, and you use stretch factor, then you see more information. So you have the same data, different representations, so it's more information, right? So you see it in there. Right, so you see now I can clearly see the bottom of the valley where the accumulation is high, and actually the places where the accumulation is low, which correspond to the regions. Right? So it's much better if I just change it. Remember, just select the layer and select the logarithmic mode and just pump up the logarithmic stretch factor. So I'm going to show you now the difference, and we're going to create a new layer, which is a fake layer, fake DM. I'm going to create a fake DM, and we're going to just do the same thing, the same calculation on that fake DM. And I'm going to show you the difference between that multiple flow direction algorithm and the very, very basic D8 algorithm. And you're going actually to see how the different, how the catchment area is different. So we're going to go to, let me see if I find it. This one of the most different thing. We're just trying to find actually. Yeah, geometric figures. Okay, in Greek calculus, it's geometric figures, and that's going to create a fake DM that actually has a geometric shape. And we're going to create a cone, right? We're going to create a cone, and we're going to work with a cone. So geometric figures. I leave it in cell count, which that's the size of the grid system, 100 by 100, right? Cell size 1, I haven't heard about the cell size actually. And a cone up. It's important that it goes up because otherwise it's going to go down and it's going to be a big sink, so that's useless for it. Cone up, right? It's going to be like kind of Mount Fuji, one thing like that. Bit. And now you see I have a new grid system, right? Cell size of 1, 100 by 100, with the lower left corner makes it 0, 0 coordinate. So I have my cone, and now I'm going to do the same analysis but using the cone, right? So let's go. I just go back to the hydrological model, catchment area. Sorry, no photo. Parallel. I select the order, right, and the elevation, the cone, right? Now I'm calculating things in a cone, which is like an artificial surface that I have here, right? And I create, this catchment area with the multiple flow direction. I'm going to use the multiple flow direction for that with my cone. Boop, boop. Okay, it's the cone. I'm representing, and you see that's how water flows. That's a pretty real thing. Like you have a cone, right, and you drop water, and it spreads like pretty evenly, like that. Water goes everywhere. Like you have a cone, it's completely symmetric, like this circular symmetry, and you just drop water, and it goes everywhere. Right. Now let's do the same, but using the D8. Right? Let's use the D8 method. So we just go and use the catchment area. Let's keep everything the same, so it's going to override the other one, and select here the D8, deterministic 8. Now water cannot flow in any direction. This water can flow in the multiples of 4 to 5 degrees, just like north, east, or northeast, west, etc. Okay. You see the difference? It's terrible, right? It's a great difference. Now water doesn't flow as it should. Yeah, it's like this is the way that water flows according to the D8 model, which is not very realistic, right? Because that's completely symmetrical. And here it says that water flows through these channels, and there's no water anywhere else, right? So you see that's the difference between the methods, and you have to take that into account. If you use basically any other software that is not SAGA, basically it uses the D8. So if you go to RTS, if you go to any other thing, basically it uses the D8 because it's the easiest one to implement, and it's the one that you're going to find usually, right? But you see the difference, it's clearly a big difference, right? All these methods are more theoretical or more like these papers, but SAGA has them implemented and differently made it. That's important, right? No problem. Any question there? Okay. So, cool. I'm going to move now to what we're going to do, to follow that, is like the overview. I'm going to try to create a channel network now, which is a vector layer based on that, and then I'm going to create sub-basins. I'm going to divide all this territory in different watersheds just by keeping on doing things, right? But there's another one thing that we have to take into account. I warn you that you should feel the sinks, right? When there are sinks, you have to feel the sinks. We already did that. But now there's a second problem, right? And which is that problem? Let's go back to the catchment area. So this is our DM, and one of the things that we did when we, for the catchment area is, as I said, we take all the water that comes uphill, right? So if I want to know the catchment area in here, right, what I do is just go up, and then I take all that area, right? That's what I do. Okay, imagine that I'm here, okay, and I take this small thing, and I have a lot of flow accumulation, right? My flow accumulation it's very high in here, right? Because all this water is flowing into here, right? And now I see this little thing that I don't have a lot of accumulation in here, right? Because, well, the water flows into here, it's just this little thing in here. And I don't know what is here. But what happens if uphill in that area that you do not have in here, in this area, I have a massive river? What happens if the whole Amazon River is flowing in here? I don't know, because I don't have that information. Okay, and that's a problem, and that's what is called edge contamination, right? So if when I'm calculating this accumulation, I go up, and this up, I reach the border, then I cannot take the value as a good one, because I don't know what is beyond the border, right? I don't know if this is just one single cell or the whole Amazon River. Okay, so all those areas that are affected by this edge contamination, we shouldn't use the catchment area in there, right? And how do we know which areas are affected by edge contamination? Well, there's a module in SAGA that actually calculates the edge contamination. So this is what we're going to do, just so you're sure. In this case, then we're going to see that it's pretty easy that if we're analyzing this place in here, the whole basin is inside, and we're going to see it, so there's no problem with that. But it's important to have that into account, because you cannot make any analysis. It's like, okay, I analyze this, and then I'm taking into account the part that I'm missing. No, you have to always take everything into account, right? So there should be in hydrology, the edge contamination, right? And after we select this, put our elevation in here. Of course, the elevation has to be filled because we're going to do hydrological analysis, so we need to have those things. And it's created bottom version, which you will say it's not a very nice layer, it's a very ugly layer. Okay. Well, we just basically see all the things that is not blue, everything that has a value of 0, it's contaminated. As simple as that. Right? So here, in these areas that have a value of 0, when you move in here, you see that the value in the lower part of the window, you see the value when you move the mouse over. So all these areas with 0 value, they're fine. That means that if I start going uphill, I don't reach the border. So everything that is actually flowing into there, I know about it. But in this area in here, I'm not. Right? And this values mean actually the number of different cells that I reach in the border. Right? So all these areas in here, I don't have to use that value because that's not a good value. So I can just work. If I'm doing hydrological analysis, I should stay within this. Right? Not in this area, not in here, not in here. Okay. This case is not very bad, but in other cases you might see that if I cut, like in here, everything's going to be affected by edge contamination. Right? So that means that I can take those values for further analysis. Okay. Just to show you, we're not going to use that anymore. But it's a good thing that you have to check whenever you work, right? Okay. So let's move to the next step, which is actually trying to extract the channel network from there. So we can see that in these we can actually see the rivers there, right? We can more or less figure out what they are. This is the main river, okay? And this is like the sub rivers. You know, we can more or less see where they are, but we actually do not have a layer that actually tells us these are the rivers, and it's a polygon layer, sorry, a vector layer with lines, which is much easier. You can measure the rivers, you can do other things. So it would be good to have something a little bit, you know, better than that, actually, to have some river. We can. And to do that, we are going to use another module that is called channel network. It's in this group called channel analysis, channel network. And what is the idea of this channel networks? There are many parameters that might help me see where the channels are. If we remember, we were working with the convergence index, and also in the convergence index layer, we could see where the layers were, right? And in this layer, we can also see. So any layer that gives us information about where the channels are, we can use it. Let's see how we fill the information here. Okay, so we select our. Now this is one of this is one of these algorithms where we need several layers, and as I said, they all have to be in the same grid system. That's not a problem because we have calculated them all. But if you have one DM coming from somewhere, and then you have a catchment area layer coming from a different place, you can use it together if they are not in the same grid system. It's not a problem in this case, as I said. So you select the elevation. Okay. I'm not going to use this one, which is a different one. It's not mandatory, just going to use the mandatory. And then they have this initiation grid, right? Which is the initiation grid? The initiation grid is actually the grid that contains that extra information, right? The grid that I can look at it and say, hey, here are the rivers, right? And in this case, I'm going to use the catchment area, right? I'm going to be able to take this catchment area layer and find out where the rivers are just by looking at the catchment area, right? So I'm going to select in here the catchment area, right? And now, how do I tell SAGA where to find rivers? Well, I'm going to use the criteria that I put in here in the initiation type, and in this case I'm going to say all the values that are greater than a given value, those are rivers. And those cells that do not have a value higher than that, greater than that, they're not going to be rivers. Right? So in this case it's pretty easy. You see, it's like if the value is high, which is in blue, that's a river. If the value is low, it's not a river. Like where do I put the cut? Where do I put the threshold? Well, then I can select whatever I want and I just can test. And we're going to do some testing with that. So we're going to start with 1 million, right? What does that mean, 1 million? Remember I told you we have calculated the catchment area, and the units of the catchment area are the same units as the cell size. Cell size is in meters, so the catchment area is square meters. So if there's more than 1 million square meters uphill, that's a river, because I'm receiving water from such a big area, and that's going to become a river. If there's less than 1 million, no, then there's not enough water to make a river. Okay. I can leave the other things empty more or less, and I'm going to. This is going to generate 2 layers, basically 3, but 2 of them are the useful ones. The channel network is a raster layer, it's a grid, but then it's going to generate a channel network, which is a vector layer of shapes. So it's going to generate both of them, raster and vector. Okay. Let's go for it. Okay. So now you see, this is our first vector layer. It's in a different way. There's no grid system. It's just layer. Okay, vector layer, type line, channel network. So I can just double click on it. And instead of putting it on a new map, let's put it on top of the DM. Okay, so here we select the DM1, so right, the one that we have, and just put it on top of it. So we see there's, now I have 2 layers in this. I can go to the map, And I see this is the mountain here. Alright, let me show that. Okay. So you see actually there's all the maps, and this first map, it has two layers, right? The DM and the channel network. Okay, so basically all these lines that I see here, they correspond to all the cells with more than 1 square meters upstream, right? What happens if I change that value? If instead of 1 million, I put 10 million. Yeah, then it's going to be different, because if here it's 1 million, 10 million is going to start a little bit more download. So I'm going to get a channel network that is not so dense. Okay, I'm going to have one that's more sparse. What if instead of 1 million I select 100,000? Then it's going to have more rivers, because rivers are going to start a little bit more upstream. And we're going to see. Let's go back to the module and let's run it again. We do the same thing, but just change it, right? Let's remove 1 0. Okay? So I just leave everything exactly the same. It's going to select the channel network layer that I created before, so it's not going to create any one, it's going to overwrite what I had, and that is going to be reflected on the visualization in there. You see? Now the channel network is more dense, right? So what I'm doing is just calculating the channel network based on the values of the flood conversion, right? Let's go back to the other value and use this method. So the thing that you might be thinking now or asking is like, okay, how do I select a good value? Why do I always have to try with 1 million, 10 million? Well, the thing is you have to first try it. This is a trial and error thing. So you just try, and also depends on what you want to do. If you're going to, let's say you're going to analyze something that happens at a small scale, or something that is, you know, you really need a lot of detail, then you use the low value and you get more things. If you're going to analyze a big watershed, the watershed of the Volga River, then it doesn't make sense to do that, because you're going to have thousands of little rivers that, yeah, might not be useful, and you just want to have the Volga River, 5 or 6 sub-rivers that flow into it. So it depends on what you want to do. You can do that. Another good thing is that if you know more or less where actually the river begins, it's like, no, this river, I know that it starts a little bit more down there. So then you have to use a higher value, so the header is going to move down here a little bit, right? So I'm going to go back to the previous value. Why I'm doing that? Because I'm going to go to the next step. I'm going to use these channels to create a division into watersheds. Right? I'm going to divide that watershed into different watersheds. Right? If anyone has questions, feel free to stop me. We can just, going on non-stop on that. I have my schema of things, but you can stop here. Okay. So now we have the channels. We have the desalination model and our channel network, and we can go that step further and get these polygons that actually have different divisions, subdivisions, watersheds, so I can analyze them separately. And this is what I'm going to do. Okay. So I'm going to go to watershed basins, that one here. I'm going to just use watershed basins. And why do I need a channel network? I need a channel network because what I need is to tell SAGA in which points I start all the watersheds, what is called the closing point of the watershed, the outlet. And the way of telling SAGA about that is by using the channel network. So each point where two rivers cross, that is going to be the outlet. It's going to be one outlet here, one outlet here, one outlet here, and then it's going to divide the basin so I can get the area that flows to that point in here, the area that flows on that point, etc. Now you're going to see it. That's pretty visual. So I select the grid system as usual, I select the elevation as usual, of course has to be filled. And I select the channel network, which is not actually that channel network that I'm seeing because that's the vector one. I'm going to use a raster one, right? But I haven't visualized the raster one, but I'm going to use it anyway. Not the channel direction, but the channel network. And it's going to create watershed basin, right? If I, instead of selecting that minimum size of 0, I put any other size, if there's a basin that is too small, it would join us to the closest one, right? If I put 0, it's going to calculate all the watershed, even if they're very small. So I can end up having like tiny ones with 1 or 2 cells. Okay, over. So I have one new layer, watershed basins, and here it is, alright? So let's have a look at that, but in a different way. So when I'm talking about geomorphometry, but let's do something more with SAGA, because you're familiar. You said that you have heard about SAGA, but not really familiar. So let's try to get a nicer looking map from SAGA. If you remember, when we saw the aspect one, I said that this looks like a shaded relief. It's not actually shaded relief, but it looks like a shaded relief. So we're going to calculate a shaded relief, which is a very nice looking visualization of a DM, and then I'm going to mix it with that one so we can actually see the watersheds, and we can actually see that they represent an actual watershed and all the water that falls into a single point. So I'm going to go to models, and I'm going to go to this group here called lighting visibility, which is a different way of terrain analysis related to light and how visibility is calculating that. And I'm going to use this analytical field shading. What is that exactly? The analytical field shading is going to take the source of light, which usually is the sun, and it's going to analyze how shades are produced. So that is like, I'm going to see my flat DM sort of like if I took it in paper and I actually had some relief, right? This is pretty easy. Same again, you know, it's pretty easy. Once you understand one of the models, it's pretty easy to understand the others, as long as you understand the formulation. So I select the elevation, and it's going to generate the analytical shading. And basically I can tell where is the sun. If the sun is just coming from that way, and it's at this point, or coming that way, and it's pretty low. So that's the azimuth and declination. If you leave these are the standard values, which makes it look a little bit nicer. It's a nice looking thing. I don't know exactly why there's some psychological reasons for that. But this angle and this declination are the typical one. So now what I'm going to do is, this new layer that I have calculated, I'm not going to put it in a separate one, in a separate map. I'm just going to put this analytical field shading together with the watershed basins. Alright? Watershed basins in here. So I just put them together, right? As the same as I did with the DM and the channels. So maps. Let's put it in there. Analytical field shading, watershed. There. And you can see in the map, right now I have this map, watershed basins, but now there are 2 layers, but one is covering the other. So I don't see the watershed basins because they are behind this relief representation. How can I make them, both of them appear? I can make this one a little bit transparent so I can see what is underneath. How do I do that? I just open this window in here with the object properties of the layer, right? And the layer that is on top, the analytical field shading, I can put transparency to 50% instead of 100%. And you see that's much better, right? Okay, so now we actually see that this is in fact the watershed. Here is the division. Everything that is in this side, it flows that way, and everything on the other side flows this way, right? And if I put, the channel network on top of all that, and I can see clearly. Well, let's put that in a different color. So you see that the same, you select the line layer in here, and I can change the color in here, of course. Blue, and I can even if I select in here size relates to screen attribute order, because each one of these segments in those lines, they have an attribute called order, which indicates the order of the channel network, the straddle order of the channel network. So if I give more size to that one, then I see that this one's going to show up in bigger line, and this ones are going to be thinner, right? So now I have a representation that is a little bit more, more informative, and I can actually see everything in there, right? Everyone more or less can produce that layer. So you understand the idea, like if you're used to any other GIS, SAGA is not so different. It's this thing that you have the data on one side, the representation on the other side, that might be a little bit annoying at first. But then the idea behind SAGA is basically to give you all these powerful computing things. And then I'm going to show you, I don't know if it's going to work in your computer, because I'm not sure QGIS is fully installed and it's going to work. But we're going to work with QGIS and doing kind of like this in QGIS, similar to that. Okay. So that's basically what we're doing, just like computing here in SAGA, and then we will see how to automate this a little bit, right? So we can do things a little bit more practical, just using the power of SAGA by doing that in QGIS. Okay, any question? Yep.
There are so many different algorithms to make new rasters. How to choose, in the list where you can choose prioritized by the complicity, like the first one is most...
No, usually not. Usually the order doesn't reflect anything, but if there's one that is better, usually that's the default one. Like if you see in the...
so the best ones are by
usually
default.
by default, yeah. If you go, for instance, to what we've done at the beginning, geometry is low. Yeah, usually by default, that's the feed. So you get a 7-bearing one, but this is not the first, not the last. It's just geometry. But usually by default, there's one that is known to me better, or if it's more useful. If you go to the flow accumulation, by default, it uses MFD. Well, I say flow accumulation and catchment area are the same thing, just don't think they're different. Flow accumulation and catchment area are different. You see that, well, in this case, no. The parallel one, by default, this because I run it before, but if it doesn't remember what you have done before, it will not show that. So by default, it uses the MFD. If you go to the manual, to the SAGA manual, although it's a little bit outdated, there's explanation of all the algorithms a little bit. And in the book that I gave you, there's explanation of those algorithms.
And in the manual?
In the SAGA manual, yeah. But of course, in the SAGA manual, but I would recommend you not go into the SAGA manual itself if you know how to do that. Just go to the book that I gave you, and then there's the explanation of the difference between methods and actually the formula. Okay, so we can keep on going, and I'm going to do a couple of things for moving to QGIS, and which is when we have calculated the catchment area, that was a raster, a vector result. We had a raster, channel network. That was a raster channel network and a vector channel network. Now we have the watershed basin, but they're rasters, they're not vectors, right? So they're just generated as a raster thing, so we can vectorize them. So I'm going to show you how to do that, so we see how to do with SAGA, something that is not actually geomorphometry, but it's practical to know how to use things and how to interact with that. So we're going to introduce to vectors, actually, and this should be in the shapes grid one. Okay, so it's from shapes to grid, from grids to shape. That's just like things that actually handle both of them. And there's one method called vectorizing grid classes. So what we can do with that is just take a raster layer, like that one, and it's going to generate a vector. one important thing that I haven't told you is that you see all the area that is white in there, right? Well, actually it's not white, that's why it's empty. Because we have been using these points in here in the channel network to define the outlet, but all these cells in here, they flow that way. So if we put water in here and it starts going, it will never reach any of the points. So there's no way we can know which layer, which basin it belongs to. So then they have the so-called no data value, right? If I select this watershed basin, you see in here you have to look at the values at 56. This is the basin number 57, this is basin number 46, and in here is nothing, right? Actually there's a value because, you know, raster layers are always rectangular like that, but there's a value that actually represents no data, right? So it's like I don't have any data for the basin. So now when I'm going to vectorize that, I'm not going to have any polygon in here. I'm going to have one polygon in here, one polygon for this, but no polygon in here. Okay, yep, start with that. And, I'm sorry, no. Now, but what happens if I select them? If I select the DM in here, what happens in there? It's going to vectorize the DM, that means it's going to create like, you know, 2,000 something, 200,000 polygons, because it's going to go to one cell. Is that okay? Is there any cell around with the same value? No, because they're different. So it puts just one small square in that. So that's not a good idea. And it should go to the watershed basin. So, okay, right. And I select here all classes, right? Because I want to take all the values, not just one single value, right? All classes. And that's it. So I should have now polygons, and I'm going to put it over here. What? Okay, so those are the different basins they have, which are, you see, exactly the same as I had before. The same as I had before, but in polygon. That's pretty interesting now for doing other things. If I want to analyze those layers separately, if I want to have a statistic about something in any one of these polygons, I can do it. If I want to have geometry or how elevation is distributed, and this is what we're going to do next. Is using those polygons, if you just click on the polygon in here and say attributes show, okay, here, so you select the vector layer, attributes show, you're going to see the attributes of the layer, and you see that there's nothing actually. There's the ID name, but these are numbers, that, you know, just an ID for each one, and the value of the watershed, which is absolutely meaningless. Okay. But what I'm going to do now is to extend that. So for each basin, I have different values. Like I have the area of the basin, so I have the perimeter of the basin, that I can calculate extra things, and I can have, for instance, I'm going to calculate some indexes for related to erosion, so I can have a good vision of what's happening there. Okay, so what I'm going to do now is to just extend this layer, right? Add new things to that. Close that. So what is the first thing I can do? The first thing I can do is try to calculate some properties of this polygons, like the area and the perimeter, things like that. Because those are pretty typical when you do hydrological analysis, how a shape factor and something like that for a basin. That indicates how water is distributed and things like that. How the basin has evolved and things like that. Okay, so I go back. Polygons, and then you have here polygon properties, right. And you see I can have polygons, and here, once again, this is not a good idea maybe to generate one new layer, so I can just put the same one, so it's just going to leave the same layer but put more attributes in that, right. So I'm going to calculate the perimeter and area of that one. So I have my polygons, and I'm going to generate a new layer on top of the old one, right? So I'm going to create a new one. Right. So now if I open the attributes, what happens? they are in the units of the projection that I'm using, right? This is in EPST23030, if I'm not wrong. So basically that's meters. Right? And this is one important thing, because sometimes, I don't know how it goes here in Russia, in Spain it's not like that because we have a small country. But if you take American data, for instance, most of the data in the United States, it's not in a projected data. So you can have a deceleration model which is in geographic coordinates. And if you have that, then most of the things that we have done today, you can do that. Why? Because if you go to the slope, this is important, probably you have a very large country, so probably you won't have that problem. So if we go to the DM, I showed you before, how did we calculate the slope? We just took, it's like, okay, the slope in this direction is the difference in the elevation, so this is this number minus this number in meters, those are meters, and then the cell size in here is 25 meters, but you have something in geographic coordinates, the cell size might be like 0.001, which is 0.001 degrees. So there's no way you can calculate the slope if one of the units is degrees and the other one is meters, right? They must be on the same unit, right? So this is a typical thing that you just think something don't work, right? It's like, you know, they're not showing the real value, right? Because it's going to give you like a terrible little slope. It's like, okay, there's a change in elevation of 11 meters in just 1 millimeter. So it's just crazy, right? So you have to take care of that. As I said, I don't know how it goes here in Russia, but like if you're familiar with American data, usually they have this not projected. You can get a DM from the American administration, and it's not in that. So you have to reproject that. There are also models in SAGA, or you can do it with whatever software you use. But make sure that the units that you have for the elevation, which are usually meters, the units for the elevation are the same as the unit of the projection that you're using, right? So it's a normal UTM. Shouldn't be any problems. Okay, so we just calculated something here in this polygons, and now they look a little bit better, right? So you have perimeter and areas right in there. So now, in meters, of course, units of the projection in meters, so it's like 7,700 meters in that in square meters. Right? Now we have some more information, right? And what I'm going to try to do now is to put there some values to tell me how the erosion is in those basins, right? So I can have a kind of a quick classification of all these different parts of my basin, so I can see quickly which one might have more problems with erosion, right? And I'm going to do that. First, I'm going to calculate one parameter that is related to erosion, which is called the LS factor. And then I'm going to try to calculate the average of the LS factor in each one of this. Okay. So the first thing they have to do is go and calculate the LS factor. And where do I find that? I find it in hydrology. LS factor. Right. Here it is. Okay, so you see there, the LS factor. I don't know if you're familiar with that. It comes from something called the universal solid loss equation. Well, usually LS means the length of the slope, and the S means the slope, which is a parameter. This is a linear parameter, but this is an adaptation, so it takes into account areas. It's basically the higher it is, the more erosion that you're likely to have due to the terrain, right? So the terrain is, and this, if you have a look at the parameters that we were using, like have a look at that. We were using the slope and the catchment area. So how can we understand that? Imagine that you're in an area where you have high slope and high catchment area. What does that mean? That means that a lot of water is coming and it's going to go fast, right? Because there's a lot of slope. So that means that you're going to have erosion. What happens if you have a lot of water coming, but there's no slope? Like, water is going to stay there and probably going to be very wet, but you're not going to have erosion, right? So taking those parameters together, we're going to calculate this LS factor. basically, if a lot of water is coming and there's a lot of slope, it's going to have a lot of erosion. Right? It's not as simple as that, but yeah, kind of. So we select the slope. We have everything calculated, right? Here's what I told before. This slope has to be in the units produced by the slope algorithm. You have slope from somewhere else. You have to make sure that it's in the same. And I select the catchment area. And this is important to select 1 divided by the cell size, because this is supposed to be used using something called the S-specific catchment area, which actually is not calculated by SAGA, but a very quick way of calculating catchment area is, the S-specific catchment area is just catchment area divided by the cell size. Right? So it's going to divide by the cell size to get this catchment area. There are several methods that we select. The original one is that. Actually, this guy, Booner, this is one of the guys that started SAGA. Right? So it's kind of the SAGA method. But we're going to use normal ones, right? Okay. Factor. Visualize that as well. You see that you see that sometimes SAGA just produces things with a normal color palette. Sometimes it has like a specific color palette. In this case, yeah, the areas without much LS factor, without much problem with erosion, are rendered here in green, and the other ones are rendered in brown, right? So you can clearly see that this is pretty mountain area, and here when the water comes, that's the flow plane in here. So this is pretty flat, and you're not going to have problems with erosion there. Like water actually stands still in there. There's a lake, in fact. Well, not a lake. That's like a pond. Okay, so now we're going to try to combine this with our vector polygon layer, right? So we can have some statistics of this LS factor in each one of those layers, right? So how can I do that? Let's try it again. Polygon. Read statistics for polygons. Now when I'm going to do all this in huge GIS, you're going to see that it's a little bit easier. The reason why it takes me a little while to find each thing is because I'm not used to use it directly to SAGA now. And you can search for them in QGIS. Here there's no search. You just have to know where they are. But grid statistics for polygons basically makes that. Polygons and grids, right? So you use grid, raster, polygon one. So it takes several grids, several raster layers, and polygons, and then calculate statistics for those grids within polygons. And we actually do not want every single thing. I'm going to just take the median. Good compromise. And this is something that we haven't seen before. Sometimes in SAGA you can select more than one grid, okay, more than one element. Usually it's like, okay, select here the DM, and there's a list, and you just click one. Sometimes you can have more than one. And usually it has this, you select the grid system, and then in here you just click on this button, and you select what you want in here. So there's this new dialog. Yeah, I'll do it again. You just select, instead of just selecting anything in here, you just have to click on this button in here, and now you select whatever you want. What do I want to analyze, to study the statistics in each of these polygons? Well, I just want to analyze the LS factor. So I just move it there and add the LS factor. Right? So everything that is on the column on the right, that's what it's going to be there. It's like one object, right? But I can have 2, 3, as many as I have. Okay, so it's going to calculate the mean value, mean in here, of all these objects. In this case, just one single object. The LS factor. Okay, let's do it. Okay.
Еще есть полигон.
the same problem?
Yeah.
Okay, yeah, because I didn't do that. Yeah. Okay. So actually, it's overwritten. Actually, I want to see that. So I see the mean factor, the mean of. Alright, so I have the mean of the LS factor, and I can use that to render actually my layer. So I can just go to the map where I have this polygon here, and I can polygon. And I can use, you see here, I select the polygons with property attributes, blah, blah, and I select in the, sorry, it's not in this casing, it's in the cloud. Oh, yeah. I select here the LS factor, right? So you see, seems that I'm going to have problems in these two layers, right? Don't have to worry about this one, I guess I can select it better. Reset. So let's have some green, red, or something like that. Yellow, red, maybe. More values. Okay. Yeah, like that. Yeah, that's better. I can just change that, the value range, so I can just, eliminate outliers or things like that, or I can just also change this mode and get to the logarithmic as I did with the given value of this rendering. Okay, so more or less you follow me, I guess. Yeah. Fine. No? One.